Hello everyone who may be viewing this video. My name is Logan Valdez and this is my lab for Physics 2 Lab 4 on oscillations. Now, to begin, the purpose of this lab was to observe and analyze a spring mass system oscillating in 2 dimensions. From that, we compared our predicted motion from GlowScript to the observed motion from Tracker and plotted the change in position and energies. Just as a quick preview of the results, the change in total energy was always zero throughout, and the predicted positions were very similar to the observed positions. The main physics principles we used were Newton's second law and the energy principle. For Newton's second law, we used F net equals ma, where F net equals ma dp over dt. From that, we used the velocity update formula. V final equals V initial plus F over m times delta t, and the position update formula. Position final equals position initial plus V average times delta t. The most important principle, though, is the energy principle. It says the change in total energy of a system equals the work done from the surroundings plus heat exchanged, and that energy is neither created nor destroyed. In this lab, the system is the spring, the earth, and the block. The surrounding is everything else. In this case, nothing. So there's no work being done on the system, meaning the change in total energy throughout should equal zero. The key equations are kinetic energy, 1/2 mv squared, gravitational potential energy, mgh, and spring potential energy, 1/2 ks squared, where s is the stretch or compression of the spring. Here's the tracker analysis. I set the origin to the base of the spring and calibrated the axes using the calibration stick from the video. You can see both the x and y positions follow a clean oscillating curve, reaching the same max values repeatedly. From this data, I got my initial conditions: x equals negative 0.113 meters, y equals negative 0.620 meters, and the initial velocity was 0. I know it looks kind of negative here, but this is kind of how it came out. Um, Let us move on. Uh, for the glow script, the computational model, the mass was 0.402 kilograms, and from the pre-lecture video, I used a spring constant of 6.83 newtons per meter and a relaxed length of 0.123 meters. In the code, I calculate L hat, and S to get the spring force. Then I compute kinetic, gravitational, and spring potential energy, so the initial values calculate F grav, F spring, and F net, and use the update formulas to step through the motion and track the change in each energy over time. Now, here are the graphs. The energy plot shows that spring and gravitational potential energy are opposite. When one goes up, the other goes down. Delta K oscillates and the total energy stays flat at zero the whole time. The position graphs compared predicted versus observed in both x and y, and they are very similar. They are very, very, very similar. The one difference is that the observed data slows down over time due to drag, while the model keeps a perfect constant period since there is no drag in the simulation. What does it mean? Energy. So, is the energy principle satisfied? Yes, the change in the spring potential and gravitational potential energy are opposite. Kinetic energy oscillates, and they all sum to zero. The total energy stays constant throughout, which is exactly what the energy principle predicts. Energy can't be created or destroyed. What does it mean? Period. For the period comparison, from the position X position data, I got an average period of 1.614 seconds, and from the Y position data, I got 1.519 seconds. They're close but not identical, which makes sense since X and Y represent slightly different modes of oscillation. The difference could also be due to drag or human error when tracking in Tracker. And that wraps it up. Total energy change was zero. The model matched the observed motion closely, and the small period difference between X and Y was likely due to drag or tracking error. But thank you so much for watching, and I hope you enjoyed this video. Have a great day. Bye bye.